Our last section from Unit 5 talks about limiting reactants. This is where we're going to use stoichiometry to determine which one of the reactants will limit how much product we can actually make. Rarely in nature are the reactants present in the exact ratios specified by the balanced equation. Usually one or more of the reactants are in excess, while one limits how much product can be produced. The amount of product depends on that one reactant. Okay, so it's much like if you are following a recipe and you've only got 2 eggs in the fridge, but you've got 3 gallons of milk, well, your 2 eggs are probably going to limit that particular recipe. Okay, so it's the same idea here. We're trying to find out which one of these reactants limits how much stuff we can actually make. The limiting reactant is the reactant that limits the extent of the reaction and thereby determines the amount of product or products formed. A portion of all the other reactants remain after the reactions stop. Okay, so what's left over is called the excess reactants. So that's the reactant left over when the reaction stopped. Okay, so you either have there's one limiting reactant and then there's one or more excess reactants. Okay, the limiting reactant limits how much you can produce, and they will always disappear completely, okay, at least for our assumptions, okay, in this class. The excess reactant, some of it will be used, but not all of it. Some of it will be left over, and we'll figure out the math behind all of this. So let's take a look here at an example of something not chemistry related. Let's say you wanted to make a bunch of tool sets, okay, and you had this many screwdrivers, this many pliers, and this many hammers. But your set of tools consists of one set of pliers, 2 screwdrivers, and a hammer. Well, when we try to divide this all out into even sets of tools, okay, we end up with some extra pliers and some extra screwdrivers, okay? Which means that when I'm trying to piece together these toolkits, really the thing that's limiting me here is actually the hammers. Okay, so if this were a chemical reaction, you'd identify the hammer, okay, as the limiting reactant. And you would say for the excess reactants, okay, those would be the pliers, I think I spelled that right, and the screwdrivers. Maybe there's a Y in pliers, I don't remember. But anyways, our limiting reactant here would be the hammer. So we're going to use this problem here as an example. We have S8, which is elemental sulfur, plus 4 chlorine, Cl2, elemental chlorine, yielding 4 S2Cl2, which is a liquid. And our question here says, if we have 200 grams of S8 reacting with 100 grams of Cl2, what mass of S2Cl2 will be produced? So it's just like going back to our pliers, hammer, and screwdriver example. Let's say that this is, 200 grams of this thing and 100 grams of this. Okay, what is the maximum amount over here that we can make? Okay, and we're going to use stoichiometry to figure that out. So really, our steps are exactly the same as they have been for our previous stoichiometry problems. We convert things to moles if they're not already in moles, multiply by the mole ratio, turn stuff back into grams, and then see which one of these makes the least amount of product. So really, all we're doing is 2 stoichiometry setups, both creating the same thing. Okay? And whichever one makes the least amount of product, that reactant was your limiting reactant, which means the other one is the excess reactant. Okay, so what we've gone ahead and done on this slide is set up our 2 stoichiometry problems. I've got my 3 molar masses for each of these up here to help me get to the answers down below. We're going to set up 2 stoichiometry problems. One where I turn this 200 grams of S8 into S2Cl2, and one where I turn the 100 grams of Cl2 into S2Cl2. And we see which one makes the least amount. So, setting this up, grams of S8 divided by the molar mass of S8, multiply times the mole ratio. I'm looking for this product. Now, if we had multiple products, we could pick a different one, okay? We would just have to be consistent and pick the same one here and here. But here we only have one option, so that's what we're picking. 4 moles of S2Cl2, since that's what I'm looking for, divided by the substance we are given here, which was S8, so it's a 4/1 ratio. The 4 there and nothing there, meaning it's a 1. And then times the molar mass of S2Cl2, 135.02. To 4 significant figures, it's 421.1 grams of S2Cl2. Okay, we'll do the same thing again, but with the chlorine. So 100 grams of it need to divide by the molar mass of Cl2, 70.90. And then turning it back into S2Cl2 again, 4 moles of S2Cl2 over what we're starting with this time, which was Cl2, 4 moles there. Okay, and then times 135.02 grams of S2Cl2 per mole, the molar mass of S2Cl2. The last step is the same in both of them, and I get 421.1 for the first one and 190.4 for the second one. What that means then is that this is, the 190.4 is the maximum amount that I can make. Okay, it's the maximum amount I can make. I can't make the 421.1. I do not have enough stuff for it. So if the question says, what's the limiting reactant? Well, the limiting reactant isn't this. That was a product. The limiting reactant is chlorine, okay, the Cl2. Okay, that's how we determine what the limiting reactant is. If the question says, what's the excess reactant, right? That's just going to be the other one, S8, because we have extra S8. So we just said that S8 is the excess reactant. What if the question says, how much mass in grams is there left over of S8? Because we started with 200.0 grams of it, but when we get to the end, there's still some of this left over. Okay, we didn't use it all. So the question is, how much is left over? And there is a way to solve for that. We're going to set up using stoichiometry, and then we'll show you one quick subtraction step, and then we can figure out what mass of the S8 is still left over at the end. Okay, so we know we're not going to use all 200 grams of this. What we're going to do is actually start with the 100 grams of Cl2. We're starting with our limiting reactant, and we're going to turn the chlorine, instead of into the S2Cl2 like we did before, we're going to turn it into the S8. That will tell us how much S8 was used. So the 100.0 grams of Cl2 divided by the molar mass of Cl2. Again, we're picking the limiting reactant. That's what we're starting with. So divided by molar mass. Then my ratio this time is 1 mole of S8, since that's what I'd want to turn it into. I'm trying to turn it into the excess reactant, divided by the 4 moles of Cl2. And then to get it into a mass of S8, we multiply times the molar mass of S8, which was 256.48, and I get 90.44 grams. What that means is I used 90.44 grams of S8. I started with 200.0 grams. So in order to figure out how much is left over, I'm going to take my initial amount and subtract my amount used, and that will tell us how much is left. So 200.0 minus 90.44. To the 10th place for significant figures, that's 190.6. So if you look at the math there, that means I didn't use about half of it, right? I used 90.44, so I have more than half of it left over. Okay, so I had lots of extra sulfur in this problem. The last thing we want to talk about here is theoretical yield and percent yield. Okay, so we did this stoichiometry, and we determined we should be making, right, if you remember just a moment ago, 190.4 grams of S2Cl2. Okay, that was the maximum that we could possibly make based on stoichiometry. Let's say a student does this reaction in lab. Now, this would be incredibly dangerous for any of you guys to do. Sulfur plus chlorine gas, okay, would not be a safe reaction to do, at least not outside of a fume hood. But let's say they do this exact same setup, and they measure the product S2Cl2 to weigh 185.6 grams. Okay? Well, what happens in reality is that you very rarely get the amount that you expect to get. Okay? Something doesn't go right, you lose some product, something doesn't react all the way, something spills out of a vessel, whatever it might be. So let's say they actually got 185.6. They didn't get this 190.4. Okay, so let's define some terms here. A theoretical yield. The theoretical yield is what you should get based on your results from stoichiometry. Theoretically, a student that performs this reaction should get 190.4 grams of S2Cl2. Okay, the reality is, experimentally, this student got 185.6. Okay, and what is the percent yield? It's really going to be your experimental yield divided by your theoretical yield times 100. All right, we'll see what this is here on the next slide. Okay, so the 190.4 grams of S2Cl2, that's how much we theoretically should have made. The percent yield, it's going to be the experimental value, which the student got 185.6 grams during the experiment, divided by the theoretical value of 190.4 grams, and then times 100. Okay, and so this value comes out to be 97.5. So they got 97.5% of the product they expected to get, which is remarkably good. For high school labs, anything really under 10%, under 10%, I should say lower than 90% is pretty average. If you get above 90% on a percent yield, you've done pretty well for that particular lab. We just our limitations with equipment and just mistakes that can potentially happen. Usually percent yields don't come out nearly as good for high school students. So that's a pretty good one right there.